In problem number 5, we are given a positively charged plate and rho, and we also know that rho is equal to the charge over the area, and it says to calculate the magnitude of the electric field in region 1. So in this scenario, we learned that when you have an infinitely charged plate, we can use a cylinder and since we know that there are positive charges coming out in each direction, then we can take the electric flux through the ends of the cylinder here. So in this scenario, we're still going to use Gauss's law. So this is for part A. We've got EA is equal to, instead of Q, we know that Q is sigma A. And this is going to, the A is going to cancel out. Oh, over epsilon naught. I knew something was missing. And the A is going to cancel out, and so the electric field is going to be sigma epsilon naught. But you have to keep in mind, this is the total electric field coming out of this circular area that the cylinder is surrounding on the surface of the plate. So if it gives us the total out of both sides, then we need to, in order to figure out just for region 1, we're going to take this total and divide it by 2. So if I just take E for region 1, it's going to be sigma over 2 epsilon naught. Okay, so then let's plug in some values. Our sigma is equal to 6 times 10 to the negative 6 over 2 times 8.85 times 10 to the negative 12. And then when you calculate that out, you end up with 300. I'll write it here. E1 is 339,000 newtons per coulomb. The magnitude of the electric field in region 2 is going to be the same because it's the other half of the total electric field. So I would do the exact same calculation, which just gives me 339,000. Okay, so for the next two parts, it gives us two charges. One is positive 6 coulombs per meter squared, and the other has a density charge of negative 6 microcoulombs per meter squared. I already did the calculation for the electric field of the positive charge here. So for this guy, I already know that it's got a electric field, and let me use my electric field lines this way, electric field of 339,000. And it's going to be the same on the other side, 339,000 newtons per coulomb on the other side. Now, it's very important that you understand that the positive charge doesn't stop at the negative plate. It actually goes through. So I'm going to draw arrows here so we know in region 2 that it's going to the right, but it also continues past the negative plate to the right as well. We know that for negative charges, and since it's the same charge density, it's also going to be 339,000 newtons per coulomb for the negative plate, but in this scenario, it's going into the negative plate and on the other side into the negative plate. And so what you can see, and I'm going to draw it negative here just so you know in region 1 what happens, is because they're equal and opposite, we can see that the electric field in region 1 has a positive electric field to the, or it has an electric field to the left of 339 and also an electric field to the right in purple of negative 339. So this ends up canceling out to 0. Same with region 2. We've got the electric field from the positive charge pointing right, the electric field from the negative charge pointing left, and that's also 0. Now in region 2, you notice that both of the arrows from the positive and the negative plate point right, so we're going to actually double our electric field in that area, and so it's going to be 2 times the electric field. In this case, I'm going to do region 2. The electric field is equal to, 678,000. I just doubled the 339,000 that we got from part A and B. So that's newtons per coulomb. And then the next part is to calculate the electric force on an electron placed in region 2. And we know that the electric force is equal to the electric field times the charge of the electron. Since we know the electric field is 678,000, you can go into your equation sheet and find out the electric charge of an electron. And that one is 1.6 times 10 to the negative 19. And you end up with a force of 1.08 times 10 to the negative 13 newtons.